Hello, can you hear me?
Yes, sir. Now we can hear you, sir.
Yeah, thank you.
Start the session, sir.
And is my screen visible?
Assistant Professor, Department of Mechanical Engineering, Kingston Engineering College, to introduce Dr. P.V. Suresh, sir.
Good afternoon, everyone here. I would like to call upon Dr. P.V. Suresh to start up this session. So I'd like to introduce Dr. P.V. Suresh, who is currently working as an associate professor in the Department of Chemical Engineering at NIT Warangal. He has received his BTech degree in Chemical Engineering from Jawaharlal Nehru Technology University, Hyderabad in 2001, and he has did his MTech in Chemical Engineering from IIT Kharagpur in 2003, and he did his PhD degree in the area of PEM fuel, that is proton exchange membrane fuel cell, from Chemical Engineering at IIT Madras, Chennai in 2011. After post-graduation in 2003, he has worked in the Department of Chemical Engineering, GMR Institute of Technology, Rajam, and has an assistant professor for 3.5 years. After completion of his PhD, he worked as a research specialist, lead engineer in Dow Chemical International Private Limited R&D Center, Pune, for 1 year and 10 months. Then he was with BITS Bilani Hyderabad campus as an assistant professor for a short time, and currently he has been with the Department of Chemical Engineering, NIT Warangal, as associate professor. His current research interest includes fuel cell, flow batteries, CO2 capture technologies, chemical looping combustion, modeling and simulation, and computational fluid dynamics. Dr. Suresh is a gold medalist in his graduation, and he was a recipient of a prestigious General Electric company's Eco-Imagination Excellence Award for the best PhD thesis in the area of green technology in 2011. He also received Best Paper Award in an international conference on race at MIT Manipal in 2012. One of his students, Mr. A. Eraya, received Indian Institute of Chemical Engineers Ambuja's Young Researchers Award for the best MTech thesis work under his guidance in 2015. He has authored about 70 publications in peer-reviewed journals and conferences, and he is actively engaged in research and consultancy projects sponsored by various agencies. He has given several talks in various workshops and conferences, and was a chair for a few sessions in international conferences at NIT Warangal. He is a reviewer for various international journals. Dr. Suresh is a senior member of American Institute of Chemical Engineers, AICHE, member of American Chemical Society, ACS, and he is a lifetime member of Indian Institute of Chemical Engineers, that is IICHE, and Institute of Technical Education. I would like to do the virtual session to Dr. P.V. Suresh. I welcome you once again, and it's up to you, sir, to share your knowledge to us. Thank you. Thank you for giving this opportunity.
Yeah, thank you very much for the nice introduction. Am I audible?
Yes, sir. Kindly.
Yeah, yeah. Is my screen visible, by the way?
Yes.
Okay.
Yes,
Okay. Yeah. So first, I'd like to extend my warm welcome to all the participants, and I'd like to thank Professor Shankar for inviting me to deliver this invited talk. And I'm very happy to share whatever little work that we are doing in an important area of CO2 capture and utilization. So we all know, coming to the topic, I think this is a very good platform to share the knowledge, because it's ATAL FDP programs are going on in many places, and I really feel that this is a very good occasion to exchange the ideas and to exchange the work that we are carrying out, and so some of them will get some ideas from this, some of them will get motivated, some of the ideas we will also get from the participants. So in all this sense, it's a very good platform to exchange our research problems and research ideas. Okay, so coming to this topic, I mean, this is a very burning topic now, and very important topic at this point of time, because carbon dioxide emission into the atmosphere, emissions into the atmosphere, they are accelerated due to increased demand for energy. And we all know coal-fired power plants are still the major sources of power generation in many other countries. And we all know our India is hugely dependent on the coal-fired power plants for power production. And because of this, these coal-fired power plants are becoming major sources of anthropogenic carbon dioxide emissions into the atmosphere. So there are different capture technologies that are available, but among all, chemical looping combustion is one of the most promising next generation carbon dioxide capture technologies. I'm not sure how many of you heard of this technology. If you are heard of this technology, it's you can follow easily, and even if you don't hear, and if you are hearing for the first time, I'll try to explain how this chemical looping combustion works. So this talk is mainly aimed at showing how to integrate this chemical looping combustion technology into coal-fired power plants, and how to analyze the overall performance of the integrated system in terms of different analysis: energy analysis, exergy analysis, ecological analysis, and economic analysis, a comprehensive analysis. So in terms of, that's why I call it as 4E analysis. Yeah, so I'll be giving a short introduction about the problem that we are trying to address, and also what has motivated us to go for this technology, and what the methodology that we have adopted, and brief results and discussion. So now coming to this, so if you look at this is a self-explanatory. This is how our modern society has developed, and our human beings are masters of the planet, and there are many species surrounding us. But among all, so with the intelligence that is provided to human beings by the God, and also with the hard work that we are doing, and with the innovations that we are creating, with all of them, so human beings are becoming masters of the planet. Humans are the masters of the planet. But how did we go there? How did we get into this position? And what are the problems that are facing, that we faced, and that are being faced by us? And how do we stay there? So the important thing is not only being on the top, reaching the top position, but being on the top position, retaining that position is very important. So we didn't go there very easily. Then how did we get there? Let us quickly look at. So there are so many contributions from the humans. So we have contributed in fertilizers. So by developing some nutrition things, I mean, developing some fertilizers, and which helped in crop production. Then we have done a lot of research, and done a lot of contributions in nutrition in terms of vitamins, and then pharmaceuticals in the healthcare sector. Then we have clothing, detergents, colorants, coatings, and housing, right? So plastics, paints, all those things. And then in terms of automotive mobility, so we have developed cars, airplanes, and all those things. And then we have an excellent communication among us, right? There are so many things we have developed in communication and entertainment. So if you take, there is a good amount of positive contribution to our modern society, right? So now coming to so because of all these contributions that are provided by the humans, we are being on the top now. But then what are the problems, or what are the challenges that are being faced by us now? So how do we face those problems, right? So let us quickly look at those problems. So the first important problem is the world population is expected to reach 11 billions by 2050. I think we have already crossed 8.3 billions by now. Now it is expected to reach 11 billions by 2050 as per the report. And because of this, there is a corresponding increase in the water, energy, and commodities demand. So it is expected that a global GDP growth over the next 50 years will be around 6 to 7 times as on today. And then the production capacity for most of the commodities like steel, chemicals, lumber, and all those things will increase by 5 to 6 times. There will be an increase in the, it is projected that there will be an increase in the energy demand by 3.5 times, and there may be some increase in electricity demand by 7 times, and there will be increase in the water demand. And because of all this, there will be also, it is also projected that there will be also increase in greenhouse gas emissions. So now because of all these problems that we are facing, now the challenges is a good definition of sustainability from Brundtland Commission, that is given by Brundtland Commission in 1987, is the ability to meet current needs without compromising the ability of future generations to meet their needs. So is our future sustainable? So we should not consume our future generations' needs, right? Also, we should, because of our acts, so our future generation should not get affected. So now coming to this point, I'll be mainly focusing, I'll not be addressing all those issues. So I am trying to focus mainly on the greenhouse gas emissions and what are the remedies that we can address. So climate change is a major issue which requires immediate attention and suitable remedial measures. So we all know the entire globe is getting warmed. So because of that, there are so many consequences, right? So we need to address this problem very, very. We need to give an immediate attention to this problem. So CO2 is, there are many greenhouse gases, but CO2 is the major greenhouse gas which affects adversely the environment. So now, if you look at the greenhouse gas emissions, the share of greenhouse gas emissions, so by different countries from the fossil fuels, and we all know with the growing energy demand, fossil fuel consumption has increased, which is leading to enormous CO2 emissions into the atmosphere. So here only few countries are listed which are major contributors of CO2 into the atmosphere. So China, United States, European Union, India, and Russia and Japan. So these year-wise share of CO2 emissions from each of these countries is shown in this table, shown in this figure. So countries such as China, USA, and European Union, so they are the leading CO2 emitters in the world, while the developing countries like India also contribute to a significant amount of global CO2 emissions. So we are in the 4th place now in the total in the major CO2 CO2 emitters into the atmosphere. So this figure shows the share of global CO2 emissions by different countries from fossil fuels during the years 2010 to 2017. So it needs to be updated by with the latest edition. So now India ranks 4th after China, United States, and European Union. with 6.62 percentage share of global CO2 emissions during the year 2017. And in the recent years, notable decrease in global share of CO2 emissions can be observed in case of United States and European Union due to good CO2 management strategies that they have adopted. And in case of China, Russia, and Japan, the share of emissions is stable, whereas it is on the increase for India because of increased power production and because of increased population, which is because of in turn we can relate it to increased population and globalization and all those aspects. So for countries like India, the problem of CO2 emissions is more critical because around 60% of electricity is generated from coal, as per the reports. So now moving on, we all know, one second, yeah. So we all know there are, what are the consequences of global warming. I'm not going to tell you what global warming is, we are all aware of that. And the consequences of global warming is, so the temperature of the earth is getting increased day by day. And if you see, these are the temperature contours, surface air temperature contours from 1960 to 2060, which are projected to 2060. And this is a climate change vulnerability index. So unfortunately, our India is also coming into this region of red or more extreme risk to high risk zone. And we can see 17 of the top 18 warmest years occurred since 2000, and 2016 and 2019 are the first and second warmest global years on record since 1880. Unfortunately, we have seen those years, and we should not wish our future generations to witness this kind of effects. And what are the ill effects of this global warming? So these are some of examples. So we have seen, we know there are extinction of species and droughts, right, and floods in some areas and uneven seasons, right. So the probability that these changes occur could have occurred by chance is virtually zero, right. But because of all our acts, because of greenhouse gas emissions into the atmosphere, and because of our problems, the entire nature is getting affected, and all the species are getting affected. So global warming by greenhouse gases has become a major concern worldwide due to its adverse effect on the climate change. And so because of the seriousness of this problem, so all the countries have met in 2015, November 30th to December 11th in Paris, in a conference of parties, COP21 conference. And about 195 countries voted to adopt a historic agreement on the climate change. So what is that agreement? They wanted to limit the global warming to 2 degrees Celsius by 2100 year. So with compromise, this is the agreement. With compromise and cooperation, all these parties, the countries which have met in the COP21. Hello, yeah. Any issue?
No, sir. You can continue, sir.
Yeah, thank you. So with compromise and cooperation, they set an ambitious goal of halting the warming at 2 degrees Celsius with measures to aim for 1.5 degrees Celsius by 2030. And to reach a 2 degree scenario, 2DS, so a 2 degree scenario of by 2100, a target level, the calculations or the projections have shown that a target level of 450 ppm of CO2 equivalent has been predicted by many models to stabilize the global average temperature increase to 2 degrees Celsius at the end of 21st century, that is 2100, right? So 450, but unfortunately already the concentration of CO2 into the atmosphere is on rise, and it is reaching So India ratifies this historic Paris climate deal on the October 2nd of 2016, so which is the 147th birth anniversary of Mahatma Gandhi. And so we there onwards, so the government has started looking for CO2 capture technologies and CO2 reduction of CO2 emissions into the atmosphere. And unfortunately, if you look at US, so it has dissented with the Paris Agreement. With US with 4.8% of world population, it uses 21% of world energy production, whereas India with 16% of world population, it uses only 3.5% of total energy production. So this is the disparity. So even though US uses most of the world energy production, it has not it has dissented with the Paris Agreement, while all other countries which are using the which are which I'm getting some noise. I mean, can I request the participants to mute? Yeah. So now, in order to achieve this target CO2 emissions into the atmosphere of 450 ppm level by 2100, then how do we achieve these targets? So a single strategy may not be sufficient. So we need a multi-pronged strategy, so which includes application of carbon dioxide capture, sequestration and utilization, CCS and CCU technologies. So we have to bring in CCS and CCU into reality, and then utilize. We also look for utilization of alternative energy sources other than coal. So we should depend on alternative energy sources such as solar energy, wind power, and geothermal, and also renewable energy sources such as biomass and biofuel. So there is a huge thrust on going for these energy sources, but they have got their own limitations still. And another strategy is the improvement of process efficiencies to reduce the energy consumption. So already existing processes are equipments, so we should try to improve the efficiency of this so that they'll consume less energy. If they consume less energy, then the energy can be utilized for some other purposes. So yeah, better efficient processes, we should design efficient processes so that they'll be energy efficient, right? So they consume less amount of energy, because we are producing energy from the coal-fired power plants, let's say, so which are resulting in anthropogenic CO2 emissions. So if you can reduce the energy consumption, right, and then energy production, so then the release of CO2 into the atmosphere will also be reduced. So now the motivation for our work is like this. So at present, so we are yeah. So India has vast coal resources, so which are amounting to about 8.3% of the total global coal reserves, and about 3/4 of electricity was produced from the coal for the year 2016 to 2017. Now, as on 31st March 2016, the estimated reserves of coal were about 308 billion tons, and an addition of 2.2 billion tons over the last year. I mean, so there is an increase in the coal reserves also, and we are leading coal. We are having the highest coal reserves in the world also. So coal deposits are mainly in India, if you take poll results are mainly confined to eastern and southern, central parts of the country. So around 70, if you look at the statistics, electricity generation by sources in India during this year, so major chunk of electricity generation is by coal, around 76%. All other renewables and alternative energy sources, so they have contributed to around 25% only, less than 25%. So as we know, there is carbon content in the coal, so obviously there will be release of CO2. So how do we address this? How do we capture this CO2, right, that is released from the coal-fired power plants? So at present, there are 3 conventional CO2 capture technologies: post-combustion, pre-combustion, and oxy-combustion. So the first one is post-combustion So what we do here in post-combustion capture is, so from the combustion, so we'll get flue gas, and the flue gas will be flue gas contains CO2, and this CO2 will be captured using post-combustion capture techniques, and then the captured CO2 will be sent to will be either compressed and stored. It will be sent for sequestration, or if possible, it will be utilized. So after combustion, whatever CO2 that is released from the flue gases, so we'll try to capture there. So it's a post-combustion technique. So this post-combustion capture techniques or units will be integrated with the conventional coal-fired power plants, the existing coal-fired power plants. So it's a retrofit technology option. But the disadvantages are flue gas is dilute in CO2. So the CO2 that we get from here is in dilute form, and it is at ambient pressure. So it will be very difficult to capture CO2 from this. So it is very energy intensive. So this results in low CO2 partial pressure, because the concentration of CO2 is less, the partial pressure of CO2 is less. Because of this, it is not it's a energy intensive process or expensive process. You can either use absorption techniques or adsorption techniques here, right? So many techniques are being attempted. Next, pre-combustion capture. In pre-combustion capture, what we do is, so we'll combust coal with pure oxygen. So there will be a gasification thing here. So coal will be gasified by supplying pure oxygen here, and the syngas that we get from this, so will be sent to a shift reactor, where it will be converted, the CO that is there in the syngas will be converted to CO2, and it will be now CO2 and H2, and you can easily separate CO2 from H2 here using any CO2 separation unit, and then hydrogen goes to combustion turbine, and then there will be power production, and this CO2 will be sent to sequestration after compression. So here you'll get so synthesis gas is concentrated in CO2 and high pressure. That's the advantage, and it is applicable mainly to the new plants, not for the existing plants. And as few gasification plants are currently in operation, and the barriers to commercial application of this on the downside, barriers to commercial application of gasification plants are common to this capture technology also. And the cost of equipment, extensive supporting systems are required in order to realize this. So that's the disadvantage. And another capture technology is the oxygen. And one more thing is, here you require pure oxygen. How do you get pure oxygen? Pure oxygen is not readily available. You have to either get it from air or from water. So again, you require air separation unit here, so which is again an energy intensive process. So another capture technique is oxy-combustion capture. Again, this requires pure oxygen, and the coal will be directly combusted here using oxygen. So there won't be any syngas production, gasification here. So it is directly combusted, and you will get CO2 and steam. And there will be a rich form of CO2 that is coming out from the oxy-combustion unit. And this can be easily separated, as this water, this steam can be condensed and CO2 can be separated. So this CO2 can be sent to compression or sequestration and further utilization. Right. So it is very high CO2. The advantages of this technology are very high CO2 concentration in the flue gas, and it's a retrofit and repowering technology option. Large, and the downside, you require a large amount of CO2 oxygen here, and large cryogenic O2 production requirement may be cost prohibitive. It is a costly process, and it's an energy intensive process, and cool CO2 recycle required to maintain temperatures within the limits of combustion materials. So all these things will reduce the entire overall efficiency of the process, so as they increase auxiliary load, right? So though these technologies result in attractive CO2 reduction by capturing them and not releasing into the atmosphere, they result in attractive CO2 reductions, but they are associated with huge energy penalties. So the post-combustion capture for the conventional coal-fired coal-based power plant, it results in around 7 to 10% energy penalty. The post-combustion capture actually results in around 7 to 10% energy penalty for 85% CO2 capture efficiency. Whereas the pre-combustion and oxy-combustion, so the other two technologies, they are for the conventional integrated gasification IGCC plants and all. So they have resulted in around 7% and 9% energy penalties for CO2 capture efficiency of 94 or 200%. So they are somewhere around 7 to 10% energy penalty in the penalty in the energy efficiencies. So thus, what we need is a CO2 capture technology, so which has lower energy penalty, right? So that is required, and that will become a more viable option than these three technologies. So in this context, and chemical looping combustion is very, very attractive, because it captures around most of the CO2 that is emitted from the power plant at a lower energy penalty as compared to these conventional CO2 capture techniques. So the chemical looping combustion, as I've shown here, so it actually shares the advantages and disadvantages of these two captures techniques, that is post and oxy combustion capture. So here in chemical looping combustion, what we do is the coal, we don't use pure oxygen here, but we use only air. So this, but in the oxygen, the chemical looping combustion, so this combustor, so that will be actually replaced with two reactors. So where you have air reactor and fuel reactor. So the fuel will be combusted using oxygen, which is supplied in the form of oxygen carriers or metal oxides, which are generally used as oxygen carriers. So the oxygen will be supplied in the form of metal oxides, and the fuel will be taking oxygen from those metal oxides, and it gets combusted, right? So you'll get CO2 and steam there, and whatever because of this, the metal oxides are getting reduced, and the reduced metal oxides will go to the next reactor called air reactor, where air will be sent to regenerate the metal oxides, reduced metal oxides. So the reduced metal oxides will be reoxidized or oxidized, and they'll become metal oxides again because of this air. So these metal oxides again, they'll be sent back to the fuel reactor. So the metal oxides will be in a loop between these two reactors, air reactor and fuel reactor. So that's why it is called chemical looping combustion. And because of this, there'll be from the fuel reactor, the outlet from the fuel reactor will be mainly CO2 and steam, and as steam can be easily separated from CO2 using a condensation chamber, so you can separate CO2 from the steam, and CO2 will be in rich form, and this rich CO2 or a rich form means it's concentrated, and this CO2 will be captured and sent to compression unit for either sequestration or for utilization. So that's what this technique is. So if you look at, so it shows two reactors, air reactor and fuel reactor, chemical looping combustion. So air reactor and fuel reactor. So coal, or it can be any fuel. So the fuel will be sent to fuel reactor. There will be metal oxides. So here I'm showing you Fe2O3 as a metal oxide, and this metal oxide, oxygen from the metal oxide will be utilized by the coal in the fuel reactor, and the combustion products will be coming out, CO2 and steam. And the reduced metal oxides, so the Fe2O3, because of release of oxygen in the fuel reactor, it becomes Fe3O4 or FeO, and these reduced metal oxides will be sent to the air reactor, where air will be sent to oxidize this reduced metal oxides. So you'll be getting again Fe2O3 there. So now those Fe2O3 will be sent back to fuel reactor. So you'll be getting nitrogen. So you are avoiding NOx and other gases along with this combustion products. So that's the main advantage that you're getting. Right? There is no direct contact between the fuel and air here. They are in indirect contact. They are not in direct contact. So because of that, you are getting the concentrated CO2 stream along with steam, so which can be easily separated. That's the main advantage of this technology. So it is a promising, cost-effective, and energy-efficient technology to separate CO2 from the flue gases with the aid of an oxygen carrier. So if you see, you don't require any air separation unit here because you are not supplying pure oxygen. You don't require air separation unit. You don't require a CO2 separation process after combustion, because you're getting the outlet from the fuel reactor is CO2 plus steam, and steam can be easily condensed. So you don't require a post combustion or any separation energy intensive separation unit there, right? So process involves the use of two reactors, air and fuel reactors, where oxidation and reduction will be reactions will be taking place respectively. So here in the fuel reactor, reduction reactions will be taking place, and in the air reactor, oxidation reaction will be taking place, and there are no additional separation units requirement in this process. I hope this is clear. Right, so that's the CO2 capture technique that we use here. So CO2, as I said, it is very attractive and it captures most of the CO2, almost 100% CO2 from the power plant at a lower energy penalty as compared to the previous techniques. So I'll also try to show you. We have done some analysis after integrating this technique, how much of energy penalty will be there. Now, moving on, we have also tried to integrate this CLC, chemical looping combustion, under three steam boiler conditions. So subcritical coal-fired power plant, supercritical coal-fired power plant, and also ultra supercritical coal-fired power plant. So we all know the lower calorific value, our Indian coal is having lower calorific value compared to some low ash content coals abroad. So our coals are mainly high ash content. It reduces the net efficiency of the power plant as compared to the low ash content coals. So one way of increasing this net plant efficiency is by adapting advanced power plant technologies such as supercritical and ultra supercritical plants. So So nowadays, we know even across the globe about power plants are based on subcritical plants, subcritical conditions. Only there are about 22% based on supercritical and 9% are based on ultra supercritical plants. So the disadvantage are the problem with this supercritical and ultra supercritical is the materials of construction, because they'll have to withstand this high temperature and pressures. So once we are those type of materials are available, these ultra supercritical and supercritical based power plants are very, very efficient compared to subcritical, right? So what we have done is we try to integrate this chemical looping combustion in all these three types, and we have shown which is a promising option. So to come up with a comprehensive analysis, to come up with a sustainable assessment, what we have done is, so as I said, we have tried to study the feasibility of integrating chemical looping combustion into subcritical, supercritical, and coal-fired, ultra supercritical coal-fired power plants. So to analyze the performance, so we have taken a we have taken 4 yardsticks. So one is energy analysis, Exergy analysis, ecological analysis, and economic analysis. So we have done all this 4E analysis for sustainable assessment of the feasibility studies. So energy analysis, why all this 4 are required? Because if you see energy analysis, this gives the efficiency of energy utilization. This gives efficiency of energy utilization, but it does not provide information about sources of losses. Whereas Exergy analysis provides whereas Exergy analysis provides the location of actual losses. So that's why these analyses are complementary in nature. Energy and Exergy are complementary in nature, and hence these are equally important. Both are equally important. Energy efficiency based on thermodynamic analysis will not provide all the necessary insights into the performance of the system. So Exergy analysis coupled with energy analysis has always been recommended, and that has been used by many other researchers, right? So the main advantage here will be by doing these two analysis, by locating the sources of energy losses. Exergy analysis also indicates the potential for improvement of the system to reduce these losses. So which are the units which are causing more loss? So that will give us clues to attack on those units rather than concentrating on other units which are resulting in which are having less contribution towards overall improvement of the process, right? So that's why both analyses are required. I mean, because this being 5th day of this course on Exergy, so all of you must already have some idea about Exergy analysis, how to do Exergy analysis. So I'll not concentrate much on that, but I'll try to show what are the results that we obtained from this analysis. Now, in addition to this energy and Exergy analysis, so in addition to this thermodynamic analysis by the way of estimating energy and Exergy efficiencies, evaluation of environmental, one more thing is an evaluation of ecological, evaluation of environmental, ecological, and economic analysis. So both are essential for a comprehensive assessment, for a comprehensive techno-economic assessment of any power generation system. So I'm sorry. So the need for this environmental impact assessment is very well documented. However, to compare this environmental impact of different technologies on an equal footing, so what is required is a cost should be assigned to the environmental benefit or degradation that is realized. And that's why from the economic analysis, what we try to do is we try to obtain the levelized cost of electricity from all these different cases. And this is the most important metric for comparison of various schemes, while the other three, economic analysis is the important metric for comparison of different schemes that you are going to propose, while the other three, such as energy, exergy, and ecological analysis, they serve the purpose of providing better insights into the weak links of this entire process flow sheet. So that's the advantage here. So economics is the most important metric for comparison of various schemes, while the other three, they provide better insights into the weak links of the process flow sheets. So that's why we concentrated on the comprehensive assessment, which involves energy, exergy, economic, and ecological analysis. So I'll not go into the details. As I said, energy analysis gives the efficiency of energy utilization. You all know what an Exergy is and what energy is. So it does not provide, energy analysis does not provide information about the sources of the losses, whereas the Exergy analysis provides location of the actual losses. So if you can find out this is the unit which is culprit here, so you can try to modify the that unit, and you can try to improve that particular unit, which ultimately results in the overall improvement, rather than concentrating on a unit which does not affect much towards the overall efficiency. So energy analysis is like testing with a stethoscope. You'll only get a feeling of whether you are good or not, whether you are feeling good or bad, right? So what is the heart rate, and that's it. So if there is something abnormal by testing this energy analysis, so what a doctor does is he or she tries to prescribe a further analysis, right? So he may ask you to go for X-ray or some 2D echogram or ECG and so on. So that is something like Exergy analysis, which actually will tell you what is the actual source of this problem, location of what is the actual location of this problem, right? So that's this. And as I said, in addition to this energy and exergy, ecological and economic analysis are also very important, right? So hence a 4E analysis of all this chemical looping combustion integrated coal-fired power plants and their comparison with respect to the conventional coal-fired power plant is not available, and that's what we have targeted. So one of the problems that we addressed is this. So that's what I'm going to discuss here. 4E analysis of chemical looping combustion based Indian coal-fired power plants of all these different conditions for efficient CO2 capture. So that the methodology that we adopted is, so we have used Aspen Plus to simulate the overall plant. We have done a plant-wide plant-wide simulations for all the three conditions. For all the conventional, we have taken 6 different cases. So the first case is about subcritical coal-fired power plant without any capture. So that we have taken from NTPC. From a source from the literature, so which has used NTPC power plant configuration. So we have taken the same configuration. So conventional subcritical coal-fired power plant without CO2 capture, and then we have integrated the CLC into it. So we have done a second case also, CLC based subcritical coal-fired power plant we have simulated, and then We have gone to conventional supercritical coal-fired power plant without CO2 capture, and which is also validated with the literature. And then we have integrated CLC with the supercritical coal-fired power plant. And then finally, we have gone for ultra supercritical conventional as well as CLC based ultra critical supercritical coal-fired power plants. We have simulated all those power plants with these conditions for subcritical, supercritical, and ultra supercritical as taken from the literature. Now, description of this power plants. So in the conventional coal-fired power plants, what we do is, so we'll take coal, we'll do some pre-processing and get the dry coal here, and that will be sent to combustor, and air will also be supplied to the combustor. So we'll get hot flue gases, and this hot flue gases so will be sent to HRSG section, heat recovery steam generation section. So where steam will be generated by utilizing the heat from the hot flue gases. So hot water, water will be sent here to generate the steam, and this steam, which is taken at high pressure and intermediate pressure and low pressure, so that will be sent to steam turbines to obtain the power. Right. So this is the actual conventional coal-fired power plants. Now, so after extracting the heat from the hot flue gases, what are we doing? We are just releasing this flue gas into the atmosphere. So there is no capture unit here. Now, what we have done, what modification we have proposed in CLC-based coal-fired power plants is, so this is seen. This combustor unit, now the entire combustor unit is being replaced with combination of two reactors, air reactor and fuel reactor. Usually these reactors are fluidized bed reactors. So coupled fluidized bed reactors are circulating fluidized bed reactors. So this is air reactor is a fluidized bed reactor, fuel reactor is a fluidized bed reactor. So both are coupled. Now, so here to the fuel reactor, we'll send Fe2O3. Fe2O3 is the metal oxide I have shown here. So there are different types of metal oxides that are tested in the literature. There are around more than 800 metal oxides prepared, and there are different synthesis processes, because the heart of the process is metal oxide again. So we should have better life of metal oxides for the overall efficiency of this configuration or process. So the Fe2O3 will be sent to fuel reactor, so where this coal will be sent, right? And here the coal will be oxygen from the Fe2O3 will be utilized for the combustion of coal, and this Fe2O3 will get reduced, and the reduced metal oxide Fe3O4 has gone to air reactor, where air is sent, and because of this air, this Fe3O4, it gets regenerated, and Fe2O3 will be formed, and that Fe2O3 will be sent back to the fuel reactor. And the depleted oxygen air with depleted oxygen content will be sent to gas turbine here, right? And the flue gas that is coming out from the fuel reactor, so it is going to, it mainly contains now steam and CO2 that goes to HRSG section here. HRSG section, right? So now you can again use, there is a hot gas that is coming out from this. You can have a gas turbine, and you can use this for generating power. And after, you can also send all this, these are seen again, feed water you can send to HRSG to generate steam, and this steam will be sent to steam turbines to generate the power. Now cold flue gas that is coming out from the HRSG will contain steam and CO2 that goes to CO2 separator, which is just a simple condenser which can condense steam, and you'll get CO2. And this CO2 will be going to a compressor for storage or sequestration, or you can further utilize it, right? So that's the scheme that's the scheme that is proposed. And this is the configuration here. So as I said, this is the subcritical coal CLC based chemical looping combustion based subcritical coal fired power plant. So these are the air reactor and fuel reactor. So there are high pressure and intermediate pressure and low pressure turbines, right? And these are all feed water heaters, right? So all these things are simulated using Aspen Plus. So this is CLC based supercritical coal fired power plant, and this is CLC based schematic representation of CLC based ultra supercritical coal fired power plant. And this is the Aspen flow diagram. Aspen Plus has got a facility to, we can use that particular software to simulate all those units. So we have separated into different hierarchical blocks. So this is a sizing, and this is combustion unit, so which contains air reactor. This is a conventional coal-fired power plant, so we have used a combustor here. And then HRSG section, so which contains series of heat exchangers, and then turbines, and then you have feed water heaters. So this is a conventional coal-fired power plant. So in CLC-based coal-fired power plant, the modification that we have done is we have replaced this combustion unit with CLC gas turbine combination. And we have in conventional coal-fired power plant, there is no CO2 capture, whereas here the cold flue gas that is coming out from the HRSG will be sent to a condenser and then to a compressor. So that's why we have used CCS unit here. So these are the two modifications that we got. So this CLC, it is simulated with two reactors, air reactor and fuel reactor. And this is a separator with turbine compressor, CO2 compressor. So these are some of the conditions that we have used. Some of the operating parameters of this fuel and air reactors are optimized. We have carried out some sensitivity studies to find out what is the optimum temperature and pressure of operation. And these are some of the conditions. And some of the models. The models only the limitation of this work is the models that we have used in Aspen Plus are equilibrium-based models. So they are not realistic. They won't give you a complete picture of the real model, but they are based on the equilibrium-based conditions. So they are conservative. They'll give a slightly higher estimates, but still we'll get overall idea of the efficiencies. So as I said, we have done all this 4E analysis. So we try to calculate what is the overall energy efficiency, net and gross efficiency, and net efficiency, and gross Exergy efficiency, net Exergy efficiency. And we all, in addition to calculation of overall gross and net Exergy efficiencies, so we also try to calculate individual unit-wise Exergy efficiencies to find out where the Exergy destruction is more, where the Exergy loss is more. So that from the analysis we can further use that information to improve the overall Exergy efficiency of the plant. So we also have, as I said, the ecological analysis. We try to calculate what is the amount of CO2 that is liberated, what is the specific CO2 emission rate, and what are the annual CO2 emission rate from the power plants, and how much of CO2 is captured from the released power plant. So how much of CO2 is being avoided, emission of how much emission of CO2 is being avoided because of this capture. So that we try to calculate. And as I said, we have also done some preliminary economic analysis. We try to calculate what is the total capital costs and operational maintenance costs of different equipments, and by considering, of course, the cost figures obtained are not absolute. They are mainly because the data that we have. There are some uncertainties in the equipment cost data, uncertainties in the values of oxygen carriers, cost of all oxygen carriers and other prices, fuel prices, and uncertainties in the value of capacity factors that are available in the literature, right? And exclusion, we cannot include all the small minor equipments. So some of the minor equipment are being excluded. So because of all those things, the figures may not be very accurate, but they'll give some rough estimate. They are not there can be some uncertainty in the overall cost calculations. So the results obtained can be used. So because of this, the results obtained can be used to study the potential and economic feasibility of CLC integrated plants against conventional technology. So what we have done, all those uncertainties are common in conventional plants as well as in CLC based plants. So if you just ignore these things, then you can compare the conventional coal-fired power plants against this coal-fired CLC-based power plants on an equal footing, right? So that's the idea. So this is how to calculate all this is already available in the literature. You can see. Yeah, as I said, to have a common factor, we try to calculate what is the levelized cost of electricity. We ultimately are getting electricity from all these 6 cases. So we try to calculate what is the levelized cost of electricity from all these plants. So we have also calculated the levelized cost of electricity by considering something called social cost of carbon. If you see social cost of carbon, it is a measure of economic detriment from the impacts that are being created by the emission of CO2 into the atmosphere, which are expressed as to the atmosphere. So as we all know, now you see, if you just leave CO2 into the atmosphere, then our country is going to pay a penalty, right? So there is a cost that is given because of this release of CO2 into the atmosphere. You are actually damaging. There is a lot of damage that is happening, right? So that can cost families, business, governments through increased food prices. They may really. So all these things are accounted, and a cost has been accounted for a cost has been defined as social cost of carbon, and I mean, in 2018 there was a report by Riquet et al. About all this social cost of carbon for different countries, and for India, $86 per ton of CO2 emitted has been given. So this social cost of carbon is also considered in our present analysis. So if you release 1 ton of CO2 into the atmosphere, this is the penalty that you are going to pay. So that is ultimately that is resulting in your increased levelized cost of electricity, right? So that is also being accounted in our calculation. So these are some of the assumptions. Yeah. So as I said, all the 3 models, conventional coal-fired, because we don't have CLC-based coal-fired power plants yet, right? So we have conventional coal-fired power plants on subcritical, supercritical, and ultra supercritical. So we have first simulated all those plants, and we have validated all those plants with the reported literature. But CLC-based power plants are not available in the literature. So we have obtained some calculations for CLC-based power plants. So all these conventional-based power plants are very well validated. So the models that we have used we got some confidence on using the models that are available in the Aspen Plus. And we have done some parametric analysis to fix to study what is the effect of oxygen carrier, because we have to send oxygen carriers in the chemical looping combustion. How much of oxygen carrier is required? So we have done some sensitivity analysis there. And what is the effect of air temperature, and what is the effect of operating pressure? So all those things we have done, and finally we have fixed all those parameters to be 10 bar pressure and 900 degrees Celsius as the air reactor temperature. and fuel reactor temperature, and 44.7 as the oxygen carrier to fuel ratio. So yeah, as we are running short of time, am I on time, Professor Shankar?
Yes, sir. You can proceed, sir. Still 20 minutes more.
Oh, okay. Thank you. Thank you. So now, so coming to the results part, 4E analysis. So I'll show, this is the energy analysis part. So where we have shown subcritical coal-fired power plant, supercritical and ultra supercritical under each, so conventional and CLC based. So if you see, the net electric efficiency has been calculated both based on HHV and high calorific value and lower calorific value. Now, so based on these two, if you see, this is yeah. So based on HHV, if you see, the 35.88% is the net electrical efficiency of subcritical coal-fired power plant. So now, if you use a CLC-based coal-fired power plant, so it's about 34.96. So there is a slight penalty in the energy efficiency, and the penalty is less than 1% here. So if you go to supercritical conditions, so conventional coal-fired power plant has got an energy efficiency of 37.52. If you integrate CLC with this, there is a penalty of about 1.5%, and ultra supercritical there is a penalty of about 4%. But in all these things, the advantage that we will be getting is, so the conventional plants are without CO2 capture, whereas all these CLC based plants are 100% CO2 capture. They'll be capturing almost 100% of CO2 that is liberated. So, so the point here is the penalty penalty in the energy efficiency is not that high. So it is, even if you take ultra supercritical, it is less than 5%. So this is energy efficiency net Exergy efficiency comparison between subcritical, between conventional and coal-fired power plants for all this three categories. Right. So the net Exergy efficiencies of coal-fired power plants with advanced steam boilers, ultra supercritical and ultra supercritical, they are found to be more compared to both conventional type and CLC based type. So they are found to be more Exergy efficient. And in addition to this overall Exergy analysis, so what we have done is we have also done some study on individual unit-wise Exergy losses. So this is the pie chart of conventional subcritical coal-fired power plant with all different units. So what is the Exergy efficiency in all these units? So the major Exergy percentage contribution in Exergy destruction, the major Exergy destruction is being found in boilers. Yeah, so this is a table which shows the Exergy loss in different units such as boilers, steam turbine, gas turbine, condensers, and feed water heaters, aerators, and pumps and compressors. So now, if you see why we have to go for energy analysis, Exergy analysis. So one point is evident here. If you see here, the energy loss in boiler is about 125 megawatts, whereas the Exergy destruction in boiler is about 766.48 megawatts. On the other hand, if you look at the condenser, so I'm just you can compare all other units also. I'm trying to compare these two units. Condenser. So if you see, there is about 286.45 megawatts of energy loss, but the Exergy loss is only 2.5 megawatts. So what we can say here is, though large, the same is true for all other cases also. So though large amounts of energy are lost in the condensers, but the potential to utilize the waste heat energy as the useful form of work is less in condensers, and hence the improvement of efficiencies is very, very low. So though energy loss is more in these units, but the potential to convert or to utilize this waste heat as useful work is less in these in condensers. So on the other hand, if you take the boilers of all the three plants, they have high improvement potentials, as they have shown high improvement potentials here. So they have got high improvement potentials because of their higher Exergy destruction. So this actually influences. This influence is an important result of analyzing Exergy and energy together, right? So analysis of only energy would have been misleading to us to look for while we are looking for method of improving the overall efficiency. So you may end up in concluding that this is condenser is the one which is having more energy efficient, more energy loss. So you have to improve the condenser, but that is not so, because the utilization of the waste heat that the possibility of converting waste heat to useful work in condenser is less, whereas in case of boilers, that's huge. So there is a huge scope for improvement in boilers rather than in condenser. So just by looking at this energy loss, you'll be misled. If you look at the Exergy destruction, then you will get you'll be on right side, and you'll be going in right direction. So if you can concentrate on working or improving the boilers further, so you'll be improving the overall efficiency of the plant. So that's the insight that we'll be getting from studying energy and Exergy analysis together. And this is the ecological analysis. So you can see here, you can see about 672.88 kilograms per megawatt electrical energy. So this is the amount that of CO2 is being released from the conventional coal, ultra supercritical coal-fired power plant. Similarly, for supercritical, 759 and 793 in case of conventional coal-fired power plant. Right. So the annual CO2 emissions are in the order of 10 power 9 kilograms into the atmosphere. Right. So if you use that's the order in case of conventional plants, whereas if you use CLC based plants, it's almost zero. So you are not releasing any CO2 into the atmosphere. So the whatever CO2 that is generated is being completely captured. Right. So that's what the ecological analysis shows. Now coming to the economic analysis, as I said, we have calculated levelized cost of electricity from all these plants, utilizing, this is levelized cost of electricity without considering the social cost of carbon, whereas this is LCOE overall, which also includes the social cost of carbon. Now if you see here, conventional coal-fired power plant, by considering the penalty that we need to provide use because of not capturing CO2, so the LCOE is about 106.94 euros per megawatt of electrical energy, whereas in case of CLC it is 93.72. In case of supercritical it is 104, whereas the CLC is 89 and 87 here. Right. So this shows that the CLC based coal-fired power plants with supercritical steam generation technology would be economically favored option compared to conventional and other CLC based power plants. So as it is slightly more levelized cost of electricity is more compared to these two. So these options are better than definitely the conventional counterparts and also CLC based subcritical coal-fired power plant. But the issue here is, so if you can, if we can develop materials which can sustain this supercritical and ultra supercritical conditions, yes, definitely the future power plants should be based on CLC and super or ultra supercritical conditions. So if you compare, the final comparison was done based with respect to CLC based subcritical coal-fired power plant with respect to subcritical coal-fired power plant, because as I said, around more than 60% of coal-fired power plants are based on subcritical as on today globally. So what we have done is we try to compare our CLC based power plants, CLC based subcritical, supercritical and ultra supercritical power plants with respect to conventional subcritical coal-fired power plants. So now if you see, this is the energy penalty. If you compare subcritical coal-fired power plant, CLC based subcritical coal-fired power plant against conventional subcritical coal-fired power plant, there is a net energy efficiency. So the penalty is less than 1%, of course, and both in Exergy and energy. Whereas this shows the annual CO2 emission and LCOE, right? So this is LCOE overall, and this is the CO2 that is avoided. So because of this CLC chemical looping combustion, all the amount of CO2 that is generated is being avoided from its emission into the atmosphere. So in all the three plants. So if you compare CLC based supercritical coal-fired power plant against conventional subcritical coal-fired power plant, there is a increase in the energy efficiency, the energy gain. There is a gain in the energy efficiency, right? So if you go for ultra supercritical, the gain is much more. It's around 2.2 to 2.5%, right? So the choice of CLC based supercritical and ultra supercritical power plants are the promising options for the growing countries where coal is the primary energy source of energy, and the materials of construction for the steam generators and turbines in ultra supercritical plants, so that can withstand high temperature and pressure, are still under research stage now. So a lot of work is being done, is going on in developing those materials to withstand these temperatures. So once they come into reality, then this high steam generator or the advanced steam boiler plants are very efficient compared to subcritical coal-fired power plants. So if they are available commercially, then this advanced steam boiler plant integrated with chemical looping combustion would be a very favorable technological option for clean power production. So that's the key conclusion from this study, from the comprehensive analysis of energy, Exergy, and ecological and economic analysis. So the present study is intended, we have demonstrated the feasibility of a novel high pressure and temperature energetically, exergetically efficient chemical looping integrated power plants for zero CO2 emissions based on 4D analysis. Right? So we have shown that CLC based supercritical, ultra supercritical power plants are energetically, exergetically, ecologically, and economically efficient, and are highly promising options for the future upcoming power plants in near future. So the entire work has been published in Energy Conversion and Management, and we have also extended our work for cogeneration thing, where hydrogen and power can be generated, and that has also been published in Energy Journal. You can that's also available in the literature. And we also, what we have done is we also try to integrate CO2 utilization into this, in this. And one more important thing is, while calculating this energy efficiencies, we have even considered what is the energy penalty that we get, or we have also considered the energy consumption in compressing our CO2 to sequestration ready pressure. Because so the CO2 that we get capture from this, if you want to use it for sequestration will be done at very high pressure, more than 110 bar. So what we have done, we have even considered what is the energy consumption while in compressing this CO2 from 10 bar that we get from the reactor to 110 bar. So that is also being considered in the power calculations, power consumption in CO2 capture and compression. So whereas that is not there, that is zero in case of conventional, because we are not capturing at all. So whereas in case of these plants, we have considered that power consumption also. So we have done this as part of a project that was funded by SERB, and these are my colleagues, which are with whom we have collaborated, and he's a scholar who has worked on this, and he recently got awarded his with PhD degree. Thank you. And if there are any questions, I'll be happy to answer. Hello?
Sir, yes, sir, we can hear you. Participants, if you have any queries, please ask. Sir, I think there are no queries. Thank you, sir. Thank you, Dr. P.V. Suresh, sir, for enlightening us on the topic chemical looping combustion based power chemical combustion based power plant. It was a very wonderful session, sir. We gained more knowledge on your topic, sir. It will be more useful for our future reference, sir. Once again, thank you so much, sir.
Yeah, thank you. I think I'm not sure how many participants are aware of this technique. And please excuse me if I have bored with this.
No, sir, it was not a boring session. It was an interesting session, sir.
Okay, thank you.
It was, we learned new things. It was interesting, sir.
So, sir, thanks a lot for sharing your session. It's a wonderful session, and even we have learned in economics.
Yes, yes.
Yeah, in the earlier sessions, we were not able to discuss economics. So this is the session where we have come through economics. It's really useful to the researchers. Thanks a lot, sir.
Yeah, because ultimately economics is the master, right? So that has that will decide whether to go for a particular thing or not. So we thought, so at least if not very accurate, at least let us give some estimates, preliminary estimates, so which will give some idea.
Professor, have you have you researched in evaluating the net profit value for the individual plant?
Yeah, so we have calculated levelized cost of electricity obtained from each of these plants. So from there, we try to calculate what is the, we say something called payback period. So if you invest something, if you invest something, so in how many years you will get it back.
Okay, could you suggest me some best reference paper, Professor, regarding the power generation system? Because through the payback period or net profit value, most of them have been focused for the combined systems in detail in most of the research papers. Is there any important paper can you highlight?
Yeah, actually, so in the paper I have shown here, the work I presented is published in Energy Conversion Management. We have given some calculations on economics, and also there is one more 4E and life cycle analysis. Also we have done for cogeneration power plant. So there also we have provided payback period calculations.
Fine, professor. I can mail you in person and I can give that reference
Yeah.
paper. Thanks a lot, professor.
Yeah, thank you. Any other queries or questions from the participants?
Sir, I think there are no queries from participants, sir.
Okay.
Yes, thank you, sir.
I think they are in a mood of valedictory.
Maybe, sir.
Okay, okay.